Continuous exponential growth and decay. This is an expanded topic on continuous growth or decay that occurs in the natural world. What is continuous exponential growth or decay? We have worked with exponential growth and decay with whole number bases or fractions for decay and growth. However, in real world applications, the base number is not a whole number or even a fraction. The exponential growth constant is an irrational number that is represented by the letter e. E is equal to 2.718281828459, and it is as irrational as pi. In other words, it goes into infinity, never repeating the same group of numbers. E represents the base number for continuous exponential growth or decay equations. The calculation of E. The table to the left illustrates what happens to the expression 1 plus 1 over x to the x power. Notice that 1 over x has a similar look to compound interest of r over n. As x gets increasingly larger, as we can see from the table, the value approaches a number whose approximation is 2.718. Let's look at a little history of E. In 1618, E was tucked away in the appendix in John Napper's work on natural logarithms. Our next topic after exponential functions is logarithms, and we'll be learning about them. Swiss Jacob Bernoulli was the first to reveal the value of E by exploring the nature of compound interest in the late 1600s. However, the man who made E famous was Leonhard Euler, referred to as the magician. There are all sorts of myths and legends about this man and E. Euler's identity uses E in a very unique way. We have E to the power of I, pi, plus 1 equals 0. That I stands for an imaginary number. The graph of E of x looks like this. It's very similar to 2 of exponent x and 3 of exponent x. In fact, it fits right between 2 and 3. It has the same characteristics of these graphs. Please notice that the y-intercept is still 0, 1. Uses of E in exponential growth and decay problems. E is used in real-world situations, like growth of populations. Examples are bacteria, or rabbits, or anything else. Radioactive decay. Accumulation of capital, money investment. Epidemiology, plagues and epidemics. Nuclear chain reaction, pyramid or Ponzi schemes. Processing power of computers and internet content, such as the spread of memes. E is so important it has its own key on your calculator. Here's a picture of your calculator. The E key is located above the LN key. So to use E, you will need to push the blue button and then the LN key. Here we have what is known as PERT, the compounded continuously equation. P sub 0 is the initial amount or investment. We have been calling this A in our previous exponential and compound interest equations. E is Euler's constant, 2.718, or just use the E on your calculator. R is equal to the rate, and T is time. Let's take a look at our first problem. Suppose you deposit $700 into an account paying 6% compounded continuously. When you see these two words, compounded continuously, that tells you that you're using Euler's number E and that you want to use PERT. Okay, how much will you have after 8 years? What is going to be our initial value? That's right, our initial value is $700. What's going to be our rate? The rate is 6%. How much time are we looking at? We are looking at 8 years. So this is what our equation looks like. Notice that it's 700, Euler's number, to the exponent of 0.06 times 8. And then we would just plug that into our calculator, and we would have $1,131.25. So that is all you're doing for these problems. Let's take a look at another problem. Suppose you deposit $1,000 into an account paying 5% compounded continuously. How much will you have after 10 years? What is our initial value? That's right, $1,000. What is our rate? The rate is 5%. Correct. How much time are we looking at? 10 years. So this is what the equation looks like. Please use your calculator and put it into your calculator and give me an answer. That's right. We've earned $1,648.72. All right. Besides exponential growth, we also have decay. The percent of change, which is R, but now incorporated in the E, is a continuously occurring during the period of time, which your periods of time can be yearly, monthly, weekly, hourly, whatever you want to look at. We're looking at continuous interest, which we already looked at, and then radioactive half-life. Notice that the exponent can be a plus or a minus, okay? So Y is your final amount, A is your original amount, K is the growth rate constant, and T is time. Let's take a look at example 1, okay? Continuous exponential growth. Y is equal to AE K to the KT. We're looking at a population of rabbits growing continuously at 20% each month. If the colony began with 2 rabbits, after 16 months, how many rabbits would exist? There's 2 rabbits to begin with. Our K, in this case our constant, which we called R last time, is 20%. So when they tell you that somebody's growing continuously at some percent, that is your constant, your K. Our time that we want to look at is 16 months. This is what the equation looks like. 2 times e to 0.20 times 16. And if you plug this into your calculator, what will you get? That's right, you'll get 49 rabbits at the end of it. Okay, let's take a look at Jill's invested $1,000 into a CD account that claims to compound continuously at 10%. After 4 years, how much does Jill have? What is our initial value? 1,000. What is our K? That's right, 10%. And our time is 4 years. This is what the equation looks like. Please go ahead and put this into your calculator and solve. So after 10 years, Jill will have $1,491.82. Now these are all exponential growth. Alrighty, here we go. Continuous exponential decay. Please notice on the equation A, e to the negative kt, that you have a negative in the exponent. This is very important. This is what's going to make it a decay curve. So a quantity with an initial value of 7,800 decays continuously at a rate of 0.1% per hour. What is the value of the quantity after 1.25 days to the nearest hundredth? Okay, our initial value is 780. What is our rate? That's right, our rate is very small. It is 0.001. Now then, here's the question. We're looking at 1.25 days. However, it gave us the rate per hour. How many hours are in 1.25 days? That's right. 1.25 days is 30 hours. All you had to do was take 1.25, multiply it by 24 hours, and you would get 30 hours. Okay? This is what our equation then looks like. Not quite. The 1.25 should have 30 in it. Okay? And when you plug it into your calculator, you'll notice that the decay is small, over 30 hours, because the rate is so small, 0.001. All right, example 2, decay of atmospheric pressure. The atmospheric pressure P decreases with increasing height. The pressure is related to number of kilometers h above the sea level by this formula. So the pressure by height is equal to 760 E with a constant of negative 0.145 times whatever height you are. So if you want to find the pressure at sea level where H is equal to 1, notice that it's 760 e to a negative 0.145 times 1, or you get 657.42. What if we want to find the pressure at a height of 7 kilometers? We would put in the 7 where the H is at, go ahead and multiply everything through, and you get 275.43 in pressure. That's all. Thank you for your participation.